Good morning. My name is Lex van Geen. I'm a geochemist at Lamont Doherty Earth Observatory. On behalf of my co-authors, Sanur Salehin, an app developer based in Dhaka, Nadia Jamil, a PhD student at Montclair State University, Imtiaz Chowdhury, a research associate, and Professor Kazimatin Abed of the Department of Geology at Dhaka University, I'm going to try to show you how the widespread use of smartphones in rural Bangladesh could help drastically reduce arsenic exposure throughout the country. For context, let me start by showing you a map of the country with the distribution of arsenic in wells. This map is based on almost 5 million well tests conducted with the field kit between 2000 and 2005. What you can see is that the southern portion of the country is particularly affected. The red areas correspond to regions where more than 80% of the tested wells did not meet the national standard for arsenic of 50 ppb for arsenic in drinking water. The proportion of the population exposed to 10 ppb, which is the World Health Organization guideline, is even larger. In 2000, on the order of 57 million people were estimated to be exposed above this level. This declined in 2009 to 52 million and declined further to 40 million in 2013. Sadly, a more recent survey that was conducted shows that there has been no further decline in the proportion of the population exposed to arsenic. Zooming in on the area within the yellow outline on the left side, you can see that this sort of spatial variability is preserved at smaller scale, especially around the margins of the red area. This area includes Area Hazar, the Upazila, where Columbia University, with the University of Dhaka, launched a large study of arsenic in drinking water and its health effects in 2000. This slide shows you some photos from the launch of a long-term cohort study, which involved the sampling of 6,000 wells over a 25 square kilometer area and the recruiting of 12,000 participants in a cohort study. The construction of a typical tube well from the area is shown in the upper right photo, where some of our team members are tagging it for long-term tracking. And another photo shows Ratan Dar, who was a graduate student at the time, who played a key role in helping us launch this study and is now on the faculty at York College of the City University of New York. This is a map showing the distribution of arsenic in these 6,000 wells used by the cohort in 2000. What you can see is that over half the wells did not meet the national standard of 50 ppb arsenic in drinking water at the time, and only a quarter of the wells actually met the WHO guideline for arsenic in drinking water of 10 ppb. The good news is that almost 2 decades later, when the wells used by cohort participants were tested again, almost 2/3 of these wells actually met the WHO guideline for arsenic of 10 ppb, and only about an eighth of the wells, which is still a large number of people, but only an eighth of the wells did not meet the national standard of 50 ppb arsenic in drinking water. The key question, of course, is what happened over these 2 decades, and what does it tell us about reducing exposure further in this area and elsewhere in the country? In order to understand what happened over these 2 decades, it's necessary to add the depth distribution to the map of arsenic in the study area. The upper panel here is a map of a larger area than the initial study area, showing the distribution of arsenic in 50,000 wells based on kit tests conducted by a team of 10 women over a year and a half. The panel underneath shares an x-axis with the map, the longitude, and as the y-axis shows depth in meters. What this map shows is that in 2012-13, most of the wells in the 0 to 40 meter depth range were high in arsenic. But in the 40 to 100 meter range, which is the depth range that individual households can still afford to install a well, a large proportion of the wells was low in arsenic. This is what happened between 2000 and 2019. Many households were able to reinstall their well from 0 to 40 to 50 to 100 meters, and were able to access low arsenic water because of that. But not all villages were able to do that, and so some of these villages instead obtained deeper wells installed by the government because they are more expensive, and were able to access low arsenic water this way. The app that I'm going to demonstrate to you provides this sort of information at the local scale on demand. The app is called Nolkup, which means tube well in Bangla. And Nadia Jamil here shows how to download it from the Play Store, install it on the smartphone, type in Arai Hazar, which is our study area, and zooms in on an area, Dori Sachavanti, which is a village where we have conducted a number of studies. The close-up shows the distribution of high and low arsenic wells, and the yellow circle shows indicates the wells within 100 meters of the user. You can click on individual wells to verify their status, look at the test strip result, a high arsenic well here, and eventually this feature will show the photos of the actual wells. You can also click on the upper right of the screen and show wells that are deeper than 45 meters, here all low in arsenic. Finally, the screen at the bottom shows a site score, a priority score, if you will, for intervention, which here is 28. And 28 refers to the number of red wells within 100 meters of the user. The green marker shows the user walking in that village. And you can zoom out and with the finger, move the red symbol to another village, showing here, for instance, a smaller number of wells and only 3 red wells within 100 meters. And those wells are actually also close to the larger blue circles, which indicate deep government wells that should be open for public access. We launched the Nolkup app during the last week of August with a Facebook ad campaign. The ad reached about 500,000 people, and about a third of these people spent some time looking at it. The sobering finding is that only 205 actually downloaded the app and used it. We tried to target the Arai area as much as we could, but it turns out that not all the downloads took place within that particular area. As you can see from this map, people elsewhere in the country downloaded the app as well. What have we learned from this experience, and what are the lessons for the future? First of all, I hope that I convinced you that the distribution of arsenic in well water is spatially very heterogeneous. It also turns out that it doesn't change all that much over time. We have also learned from our 20 years of work in Arai Hazar that water treatment or the supply of water through a pipe water system hasn't really impacted the exposure of the population all that much. Instead, what has lowered the exposure is primarily the reinstallation of private wells to slightly greater depth by individual households. And in some areas, deeper government wells have helped lower exposure as well. Therefore, the key to lowering exposure in the future is providing information on the arsenic content of a specific well, its depth, and its location. The Nolkup app currently provides this information to only 50,000 well tests. And as you have seen, the uptake of the app has been limited. However, the Bangladesh government, to its credit, is about to launch a large new testing campaign of 5 to 10 million wells throughout the country. These well tests will be recorded with a different app and sent to a server. This server has already been set up to interface directly with Notebook. Notebook will therefore be able to provide the test results to the local population throughout the country in real time. We hope that this combination of fairly simple technology, field kit testing, with smartphones will help reduce the exposure throughout the country in the next couple of years. Thank you for your attention.